Okay, so I'm using a new mic today. Apparently there were some audio problems at some points in the previous videos there. So trying this, let's see how it goes, and if not, then well, I don't know. I guess I'll have to type everything out by email, but that's okay. I'm joking. All right, let's figure this out here. All right. So what we've been doing so far is just working with mono-substituted aromatic rings, and there's a reason for that. And the reason is because, right, if we just start with our good old buddy Mr. Unsubstituted benzene ring, right, it's fairly easy, right? Uh, we can add one thing. Right, we can add one thing to that ring, and that's good, right? But once we have one thing on that ring, we start to see some unique reactivity with that. So for instance, let's take a look at this, right? So let's say that we started out with our buddy nitrobenzene, and we wanted to do some kind of reaction with this, so let's try and throw a bromine on there. Let's feber it up here, all right. So we start out with nitrobenzene, a very common reagent, and we try and add a bromine to it. And if we do this reaction, we find that we really only get one product, and it's that right there, which would be the meta derivative. We'll say, well, I don't want the meta derivative. I want the para derivative, or I want the ortho derivative. Well, it just doesn't happen. It doesn't work that way. Additionally, right? Additionally, we notice that this is actually a very slow reaction. Now, you guys, well, you know what? Let me write this in a different color here because this will be important. Okay. So we have two very important observations. We notice that with a nitro group, right, we add a bromine to the meta position, and it's slow. That means this reaction takes a lot longer for us to do. We'll find here in just a minute that those two observations are related, but they shouldn't be conflated, right? Just because it's meta doesn't mean it's slow, right? And I'll talk to you guys a little bit more about that in just a second, okay? So anyway, all right, we go back to the drawing board and we say, all right, well, now, right, let's try the NH2 version. Right? We'll do the exact same. All right. And now what we notice is that we get this product, NH2, and now we add a Br down here. But we also get this product. So we get the ortho, excuse me, that's the para, pardon me, in green. So para and ortho. And this is actually relatively fast. And we don't see any of the meta happen. So what in the world is going on? Does the mechanism suddenly change? No, right? That's kind of the magic of mechanisms, right? As long as we understand the mechanism and it's known, then we can apply that mechanism to the specific situation, right? So the mechanism in both cases here is still identical. And what I would do, right, if we had the face-to-face class, right, I would tell you guys to stop and draw the mechanism at this point for both of these reactions. And then see if you guys can figure out what's going on, right? So I'm going to do that here in just a second, but it'd be a good time for you guys to see if you can explain this, right? And remember, right, the whole point of understanding the mechanism, or why I'm making you guys know it and memorize and all this kind of stuff, right, is it's not that I need you guys to occupy your time. You guys have plenty of things to occupy your time with. It's because of this. It's because of this right here, right? You use a mechanism to explain an observation, right? We use the things that we understand from mechanisms that we learn, the steps that we see to explain some kind of new observation, all right? So we just presented something new, so we use what we know to kind of see if we can explain that, right? And if we can't explain it, then we have to develop a new kind of theory. But in this case, we can use our mechanism to explain this, right? So take a quick second, or even take a couple minutes, that doesn't matter, right? And see if you guys can draw the mechanisms from both of these and give an explanation as to why we see the specific orientation of meta versus para and ortho for these two cases here. What would be different about them? Why would one be slow and why would one be fast, right? That's kind of the next step to this also here, okay? So I'll be back in just a second. Maybe. Okay, sorry, I was doing a little bit of stuff behind the scenes here. Hopefully you guys had a chance to look at the mechanisms here and try and at least propose an idea as to what's going on here. Or you could have just looked in the book, right? Because that's where the answers are. Anyway, let's take a look at the... let's start with this mechanism down here for this, okay? So let's take a look at the idea of aniline and doing that reaction, right? So, I'm going to skip, okay? I'm going to skip forming the Br plus intermediate here, right? So, right, we're just going to assume that we have that around, right? If you don't know how I'm getting there, all that kind of, please go look at the other videos, okay? You're going to have to show that. I'm just trying to save space and save time and all this kind of stuff. So please, 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 go take a look at that, okay? All right, so assuming we've got our buddy Br plus around, we know that we want to put this into the para position. So let's, I'm going to mark this here, right? I'm going to mark that with purple. And let's have that swing out and grab. And then we will have this. Okay. Oops, that should be in purple. Okay. So now we're at our intermediate, right? A not unfamiliar at all intermediate to any of us, hopefully, right? We got a carbocation. Anytime, right? Anytime you have a carbocation, you stop, you look, you think, you analyze, right? So what can we observe about this carbocation? Well, let me mark this and this and then this here, right? So what's special, right? Focusing in here, right? What's special about that red carbon? Right, ignore the rest of it for just a minute, right? So just focusing on that red carbon, what we should notice, or what we should see here, is that we have a allylic, right? We have an allylic carbon there. Now, do you remember what an allylic carbon is? That's a carbon that is next door to a pi bond. Now, why is that special? Well, that's kind of the, I guess, theme of this chapter, is this idea of can p orbitals talk to each other? Now, I know I did this in class before we had to go to online only, so hopefully you have your notes from there. But remember what we talked about with resonance structures and molecular orbital diagrams and all this kind of stuff, right? Our two yellow and our red carbons there still have open p orbitals. Excuse me. Let me rephrase this. Our yellow and red carbons there have p orbitals that can talk to each other, right? Essentially, right, what we're saying here is I can draw a resonance structure, okay? Let me zoom out here. Maybe. I don't know why my computer doesn't like to zoom these days. Yeah, one thing at a time, right? We're good. We are good. So we moved here, here, and here. Now, hopefully, right, you guys see, right, that we kind of set up, well, let's do this in green just for argument's sake, right, and then I'll do this one in red again. Now, hopefully you guys see, comparing the green carbons there to the red one, that we have another allylic position, and we can do another resonance here, okay. So far, right, nothing unusual, I would say, at all, right? We're just doing resonance structures and stabilizing, right? Stabilizing a cation. And just for argument's sake, right, let's go ahead and finish this up. So Mr. Generic Base, okay, Mr. Generic Base will come in and finish up to get to our product here, right? Let me get all the colors of the rainbow back in here. To red and green and black, right? Huh, okay, well, there's the mechanism for that. I'm not convinced. I haven't quite figured anything out, right? This is just a mechanism. Everything looks normal. Well, let's take a look at this particular resonance structure right here. This is where the magic happens, all right? This is where the magic happens. So let's pull this one out, all right? So I'm just going to redraw that here. I'm going to skip the colors. And I'm going to do the important thing, or excuse me, I'm going to add the important thing. Okay, now do you guys see why this is important? So we've got that lone pair on that nitrogen up there, and what can that do? Well, this can actually add, wow, bad drawings. Not enough coffee yet. All right, so we got this, this. Right? This is the important part, right? We can add another resonance structure into this mix with a lone pair on the group bound to the ring. Okay? And let me say this again, because this is I'm going to be coming back to this point over and over and over. When we have lone pairs on the atoms bound directly to the aromatic rings, the incoming groups are going to be added either ortho or para, because in those positions we can draw an extra resonance structure. Okay? Here's what I mean, right? So I'm going to go through and we're just going to quickly do the, let me pick purple here, right? Let's take a look at the mechanism for this guy in purple up here and see what I mean, right? So I'm starting off with essentially, right, the same conditions. If you guys want to pause here and take note, I'm just going to use this same set of drawings to kind of get the point across, okay? So let's get rid of that. Let's add this back in. Good stuff. Right, so that was for the para up here, right? So I'm just going to give myself some space to work. Now we're going to add here, right? So let's do a little bit of shimmy shuffle here. Okay, cool. Pi bond swings out, grabs that. And we very quickly get to our answer. Okay, and this is why I tried to keep everything together. All right, do you guys see how this resonance structure here, the ortho versus the para, right? We see we end up at a resonance structure where we have the positive charge, the cation, right on the carbon next to the atom with the lone pairs. In this case, the amine there, right? And we can draw that extra resonance structure. What is this doing, right? So this is lowering the energy, right? By having this, it lowers the energy, right, of the intermediate. And so if you take a look in the book or you look it up online, right, there's nice pictures of this, right? Remember that we can draw reaction profile diagrams for all this stuff, right? Our reaction profile diagrams are our hills and our valleys that we go through. And our intermediates are our valleys, right? If we lower the energy of the intermediates, right, then we make our reactions go faster. Okay? It's easier to do if you want to think about it. There's a smaller hill to climb over. Okay, whichever one of those ideas you want to work with. So ortho-para directors come from the fact that the atoms bound to the aromatic ring have lone pairs. Okay? Let's see how we're doing on our timing here. Okay, 15 minutes, good. Okay, so now that we kind of understand, or at least are starting to understand this point, let's go take a look at the other example of the nitro group there, right? Let's see what happens here. Why would this go meta? Okay, so start out the same way, right? We're going to start with a nitro, and I'm going to go ahead and put in the important part. And if you haven't figured it out at this point, maybe you guys can already see, whoops, I want to do that in blue, what the difference is, right? So reach out, grab this. So we have pi bond, nitro here. We add our Br here. We have our plus charge here. We resonance it up. Okay. This is blue. NO2. Br. This is now red. Right? I wish I could like tell you guys jokes while I'm drawing all this stuff out. And just to kind of keep the quiet time to a minimum. Not quite talented enough to do all that yet. It's alright, we'll get there. Wait till I figure out how to add soundtracks to this. Okay, right, so there are the resonance structures that we can draw. Who cares, you might say, right? What's the big deal? I can draw resonance structures all day long. Okay, that's good. This doesn't really help explain why it added meta, right? This just says, okay, this is what did happen, right? But it doesn't really say why it would happen. Well, let's change tactics here for just a second, right? So let me reset all this stuff here. Okay, well, no, you know what? We can do that. That's fine too. Okay, now let's, black sounds good, right? Now let's say that we did add this to the para position. Okay, so let's follow through the mechanism with this. All right, we got this, we got this, we got this, this. Got this. I should be careful, right? Drawing. Technically, when we're drawing resonance structures, right, we should put those arrows there. Okay, this and here, here, and here. Okay. Obviously, we could go through and draw the rest of them, but this is all we really need to get to. Do you guys see what the problem is here? Right? The problem is what? Positive next to a positive. So two problems with this. One, we don't really want to put a positive next to a positive, right? How many times have we seen that so far? The answer is never, okay? So that obviously is going to increase the energy of our intermediate. Okay, go back to that, you know, the fantastic hill drawing I just showed you guys up here, right? Okay. The second thing is that that nitrogen, Mr. Nitrogen here in green, right, the N of the NO2 group, doesn't have any lone pairs on it. So not only does it have a positive charge, right, as a consequence of this, it also doesn't have lone pairs, which it can use to make an additional resonance structure to stabilize that positive. So we can't, right, no additional resonance and no positive next to positive, right? We do not want to have a positive next to another positive, right? That is not a good stabilizing thing to have. So do you guys see what happens here? Why do we add things meta? Because we avoid, right? It avoids the positive next to a positive. We can add things, right? We can add things to the meta position there, right? It's just, it does this because we can avoid the positive next to a positive. Does that make sense? Now, I'm going to use my magic professor powers. I'm reading your minds, some of your guys' minds. Okay? So if you think back and you go back and rewatch this video and, kind of really go, about it, we have to be careful. Because it sounds like we're almost anthropomorphizing our aromatic rings. And what I mean is this. What I just said to you guys was that the bromine chooses to go to the meta position because it knows that it can avoid having these bad intermediates. Or that it chooses to add to the ortho or para position because it knows that it can make an additional resonance structure to stabilize it. Well, these are just molecules. They don't have sentient thought. They can't look ahead and see what happens, right? And this goes back to this idea of molecular orbitals, okay? When we draw, this is important, but not, how do I want to say this? This is really important to understand, but it might take a while for it to kind of sink in. It did for me, at least, but you guys, as I've told you guys in class, I'm a dum-dum, all right? So remember that resonance structures don't really exist, okay? They all exist at the same time, and then they don't exist, right? That's the whole point of molecular orbitals. They all exist at the same time. And what I mean, and in the next video, I'll kind of show you guys the consequence of this. Because what we're talking about here in the sense of saying that the bromine knows where it's going to go, okay, it knows where it's going to go, comes from the second part of what we were talking about. So far, all we've been dealing with are the parts in green. Why do things go ortho, para, or meta? What we're going to talk about next time is what do we mean by fast and slow, okay? Now, that doesn't mean that these aren't related, okay? They are, okay? But they are separate ideas that come together to make this whole concept here. All right? So this is getting into kind of the headier parts of this chapter. But we're going to explain it using resonance. And we're going to, in kind of behind the scenes, we have this molecular orbital stuff going on. Okay, so that's it for this video. I'll see you guys on the next one where we talk about activators and deactivators.